to Twilight, the new era of learning. This is Pack 365. In Module 2, we are discussing depth first search, algorithm in AI, Part C. Let's move to the topic. Today, we're discussing an example problem. So, in this example problem, we have DFS implementation in a robot pathfinding. In previous lecture, we discussed about maze, right? What is maze? How we find the maze in direction. Like so, in this also we have a implementation a robotic to find the path finding. So DFS can be used to find a path from a starting node to the goal node, right? So in a maze of grid-based environment, we, so it can find the own path. We have to guide that robot to how to complete the to reach the depth node. The DFS algorithm systematically explores all the possible paths from the start node and one branch at the time until it finds a path that leads to the goal, right? So it systematically explores we try to make possible as all the paths of starting nodes to end node, we reach all the paths. The below figure shows that the maze which contains that initially starts of the stage of the robot, the obstacles in the goal state, right? So I will show the image too. Wait. Here the goal node is in the position of 0 comma 5, where the robot needs to travel through the maze to find the path to reach the goal. So I show the picture of the maze. So here what we are discussing. So here we have step one. Define the maze dimensional and obstacles, right? Obstacles. So maze size. We defined a maze size representing the dimensional of the maze in our case. So it's a 6 into 6 grid, right? A list of coordinates that represent the position of obstacle which a maze is also specified. The robot is positioned at the initial state 0, 0, right? It starts from the 0, comma 0. It's a starting stage and aims to reach the goal at stage 5. So it's telling the maze. The maze is defined as a 6 into 6 grid. This means the coordinates will range from 0, comma 0 to 5, comma 5, right? It used to reach from 0, comma 0 to 5, comma 5. So obstacles is nothing but a list of coordinates representing the obstacles is specified, right? There are cells the robot cannot move into that. Okay, robot position. It's the robot position at starting state 0, comma 0. There is where robot starts and goal what to reach 0, comma 5. This is the state you want to robot have to reach. So step two, defined a is valid function. So they guys, sorry, it means here we have some small mistake. So don't color. Define the is valid, like we have is underscore valid function, right? Okay. So the is valid function checks whether a given position of x comma y is valid such that it intercept that is within the bounds of the maze and not obstructed by any obstacle, right? So here we can say that for step two, so this is a so a crucial helper function. It is a base of helper function. Before the robot attempts to move to a new position, this function checks if the move is permissionable or not. Right? Checks check permission. Right? Whether it checks performed by is valid or not. It checks boundary. It checks the boundary checks, obstacle checks. Right? So it ensured the XY coordinates of the potential new position or within the 6 into 6 grid, lies X and Y or between the 0 and 5 includes or not. So it verified that the potential new position is not one of the obstacle coordinates like that. So this is a robot I have to show it is so we have 0, comma 0 state here and up to we want to reach the final state here 5, comma 5, right? So we have to reach the goal of 0, comma 5. Okay. So if we start initial states right here. Okay. So step three, define DFS function here. So in the below code, we define the DFS functions to implement the DFS algorithms, right? It uses to stack to keep a record of the nodes and it visits and it iterates through each node that helps in exploring its neighbors, right? Recursively until it finds the goal nodes or exacts all the possibilities, right? So here selling the stack users means the DFS algorithm uses a stack data structures. A stack follows LIFO method like last in first out. In best first search, we use fee for it first in first out, but in DFS we use last in first out, LIFO. We use LIFO principles. In this context, it stores the nodes. It stores the node to be explored, right? When the DFS needs to explore a new path, it pushes the current node into the stack, right? That is the stack usage. So visited set is an empty set. It's used to keep track of nodes that have already been visited. This is virtual prevent in like we have virtual premit. Okay, so the empty stack stored the nodes to be explored, and the empty set is used to keep track of the nodes that have been already visited and avoid the retreating them. Right. So it's the virtual the visit of the prevent infinite loop. If a graph has circle and computationally it re-explore the path already no right it explore the re-explore the path if the current node is found to be the goal node, if it reverses the path so that the robot can follow and it finally returns to the path found, right? So it finally returns to the path founder. So here what we consider go and check path reversal we use here. So if the current node is been explored is found to be the goal, right? Goal node 0, comma 5 goal node. In this case, it means a path has been successfully discovered. We will discover the path, but the path is then reversed. Track back. So we use track back. So from the goal to the start, to provide the sequence of the steps to the robot should be follow the functions then return the path found. Oh, if no path is found, okay, if the path is didn't found anything, it should be returns no path found, okay. If the path found, it returns the path found. Which path it returns? If path doesn't found, it returns a no path found. So this is an executive search approach. It ensures that all the potential paths of our explorer and provides a comprehensive solution to the maze navigation problem. So if the DFS explore all the potential paths from the starting node and does not reach the goal node, right? When it does when the case of situation like this, it means there no valid path existed, right? So in this scenario, the function returns no path found. If DFS is an executive search because that it explores the all possible paths until the goal is found, right? Or possibility to extract the goals. So step 4, here we have calls DFS function to find the path. We have the output path of the goal. So 0, 1, 1, 0, 2, 0, 3, 1, 2, 1, 2, 2. Like we follow these paths in the graph. Like here we follow, like in the graph, we used to follow the paths like that. So here this telling these steps similarly indicates that the DFS function once defined is innovated with the initial state 0, 0 to being the pathfinding process. It is so output and the output like the output shows the sequence of coordinates the robot takes to reach the goal, and the output explains that section described that the path is more detailed, like visualizing the maze path. The image showing the 6 into 6 grid helps to visualize the maze like the robot icon at 0, comma 0 at starting state, the red start at the 0, comma 5 in the goal state. The crossed out circles like represent the obstacles like here we can see. So here we have starting moving like that, we have less track. So 0, comma 0 is a starting state, and 1, comma 0 is move right, and 2, comma 0 is move right again, 3, comma 0 is move right, 3, comma 1 move down. We step 1 down, and 2.1 has move left, 2.2 has move down, and 1.2 has move left again, and 0, comma 2 has move left again, and 0, comma 3 move down, 1, comma 3 move right, 2, comma 3 again move right, and 2, comma 4 move down, 1, comma 4 move left, and 1, comma 5 move down, and finally 0, comma 5 it reaches us to Google. Like here we are identifying the path. I show the path of the that's here we clearly demonstrate the how DFS explores the maze moving deep into the branch, right? Until it finds the goal or hits the dead end, then backtrack the explore of the options, right? To provide the path, the one valid found it valid. If the path is found, we mention the path found. If it doesn't, it returns back to the no path found. So here we have output explanation here. So I already explained the output explanation here. Already step one has we find the starting initial point 0, comma 0. It is the way the robot being start. Step two, the robot moves right along with the row. top row of the maze, like 1 comma 0, 2 comma 0. Again, step 3. Now the robot moves down to the second row to the position of 3 comma 1. Here the robot follows a path to left 2 comma 1, then down 2 comma 2, then right 1 comma 2, and the down again 1 0 comma 2, right? So we follow the sequence steps here, like 5, step 6, step 7, step 8. Then the robot moves right to the last column 1.5. Finally, the robot reaches the goal node at the bottom left corner, 0 comma 5 of the maze. Like we show here the maze, it follows like initial starts from 0 comma 0 initial state. We have 0 comma 0 to 5 comma 0 have like rows, and we have columns 5 comma 5, right? 5 comma. It want to the goal is 0 comma 5. Like the 0 comma 5, we start right. Again, we move down left. Again, we come down. Here, like this maze will follow the routes, right? Like the maze will follow the routes and it come back to the initial state. So it following the maze like that. The parcel. So wherever the circles were representing obstacles, matlab obstacles like we did not enter the path, right? It is a closed path here. Okay. Whenever we trigger the obstacle, it is a triggered path, right? So wherever arrows flowing, this is the path to move. Okay, move the direction. So don't think like that. It's a 0 comma 1 y with after 2 0 1.1 comma 0 2 comma 0. Y could not move to direct to 2 comma 1 because here we have a line. I am showing this graph into direct in a 2D form, but actually in 3D state, where the initial starting stage up to the border. So it has a walls like here the green lot of columns you see the green boxes. Here we have a, wall type, like we have a wall up to the 3.3 and up to the wall here to like the dead end walls we have mentioned that we are showing the graph into 2D form. So that's why we are initially taking like this. So now applications of DFS, right? The application algorithm, which is a systematical way of exploring paths by going deep by first, okay? So find the various uses in AI, right? We have maze generation. We have maze generation. The maze generation is a composite of the designing a layout from passage and walls within a maze. That maze generation makes uh, use of the randomized approaches of the depth first search algorithm because it leverages the recursive method and stack for the instance of assuming that the space is a large grid of the cell where each cell holds a four walls, right? So the concept here is the puzzle. Here we concept is telling that the mayor. Here we have puzzle solving, and what the concept of DFS is an excellent method for the systematically exploring possible solutions in the puzzle, right? Many puzzles can be represented as a state space graph where each node is a puzzle configuration and the edges represent valid moves, right? DFS can be used to search for a path, right? For the initial state to a goal state. So this is what's the concept of connecting the cells, new cells like that processing. So here we have puzzle solving too. So this also same puzzle solving includes Japanese nomograms like where we have Japanese nanograms can employ depth first search has a method for systematically exploring the possible solutions in Japan nanographs. Grams DFS is utilized to explore the different combinations of the field and empty cells. Like so, here we can take for the example of Japanese nonogram, like what they are. Like nonograms are the picture logic puzzle where you colored cells in the grid based on numbers clues and along the slides and revealing a hidden pictures, right? So here in nonograms, DFS is used to try out the different combinations of the filling and leaving the cells empty. So the explore of the one possibility deeply, if the path lead to the contraction, here we have DFS backtrack and try another combination. The systematically trials and error combinated with the backtrack. Like it is a classic application of DFS in construct satisfaction of problems. Okay. So pathfinding here we have pathfinding and roboting, right? So DFS can be employed for the pathfinding in robotics, especially in the scenario where the simplicity, memory efficiency, and adaptability are important considerations. So concept is nothing but as seen in the previous example, maze navigation. DFS can be used to find the sequence of movement, right? For the robot to get the path, one point to another point. So we have wide DFS for robot. Like simplicity is the core DFS algorithm. It retrieval the straightforward to implement, right? So memory efficiency is nothing but for certain types of the graph, especially where one of the where the depth of the search is not efficiently, right? DFS can be more memory efficiently in the breadth first search because it has only need to store the current path. So adaptability, we have DFS can be adopted to various robotic navigation scenarios, particularly those where finding any path is suit a satisfaction. Right, we can say that sufficient than the rather than the strictly the shortest one. While BFS, the shortest path is unweighted graph. Right, DFS is the option that is sufficient where the environment or task does not require strict optimally. Right? It is a little bit strict. So about the conclusion. So does this first touch embeds an crucial algorithm in artificial intelligence that offer both uh, crucial algorithm in artificial that offers both theoretical instance and the practical applications. DFS server has foundational tools for traveling complex space. As the technology evolves, DFS remains cornerstone algorithm for the driving advancement and pushing the boundaries of the AI research and the applications. So we can say in previous the maze generation we can see if given in maze generation we can see this. So in the concept we have start, random, ball remove, and push to stack, and we have backtracking, compression. So these are the steps we use in the applications where using DFS. So in this lecture, I try to explain the theoretical way of the robot concept. Okay, what are the robot of the main navigation system? It a robot how to find the path. So in practically in next lecture we did in practically we make code on it. We make particular we in practically we used to try to reach the goal. Okay, we used to starting shit and we want to reach our goal by using the code. So I hope you guys all are understand about this topic. Example explanation. Thank you all.